All right, we got like one or two things left to cover in chapter 4, and then I have an activity for us to do for the rest of the class. It'll be pretty exciting, You're going to like it. It has magnets and a worksheet. Can't go wrong with that.
I like the magnet.
All right, fair enough. All right, so the last really 3 topics in chapter 4. This is the end of tertiary structure. So tertiary structure, looking at protein folding. Is that better? Okay. So proteins will fold as soon as they emerge from the ribosome, which we will discuss later in the semester, talking about how the ribosome works and how it makes proteins. But proteins fold as soon as they emerge from the ribosome, which is where they are formed. And the protein folding is not random. The primary structure drives the secondary structure, which drives the tertiary structure. So your primary structure, which is just your string of amino acids, will then start to combine into its secondary structure by having the different hydrophobic, hydrophilic interactions, and then that drives the final tertiary 3D structure. Which means there is only one pathway. There's only one way to make these proteins successfully. There's lots of ways that they can misfold, but there's only one successful folding pattern. So in the cell, protein folding requires assistance from other proteins called molecular chaperones. And these molecular chaperones assist in folding. So we'll talk again about this more in depth in another chapter. But as the polypeptide chain emerges from the ribosome, there are chaperones there to help, like the alpha helix, right? You gotta first get around to that 1,4 interaction, so there's some chaperones that help start to curl around. Or for some of the beta sheets, they start to line them up together. So there's helper proteins that will help us get us into the right 3D structure. Then after folding some proteins, oh yeah. Some proteins require further processing. So like we've made our final 3D structure, and we'll look at specific examples of this. It especially happens in like mRNA and some of these other ones. They require either removal of amino acids, addition. Sometimes we gotta stick a lipid on the end. Addition of a lipid. Addition looks funny. Add a lipid, also true. Sometimes we gotta put a sugar group on it. So we'll have an amino acid that then sometimes we'll have to phosphorylate. Just checking. 1, 2, 3, 3. It is. It's a rough. It's been a rough week for me, just in general. Good thing I'm not writing the test this week. I'll write the test next week. right, so all those things are things that will happen after we've gotten our protein into our 3D structure. Good there? Then let's talk about our quaternary structure. So, quaternary structure, typically proteins that have a molecular mass greater than 100 kilodaltons have that mass because it is more than one polypeptide chain interacting with itself, or interacting with each other. These individual chains are called subunits. So protein may have all identical subunits. If they're all identical subunits, and that is a homodimer, any guesses on what you would call if it's all different subunits? Very good. Everyone knows their prefixes. So, two ways we could combine them together. We could either have all four the same, or they don't have to be all four different, but the idea is they're either all the same or not all the same. It's okay. Oh, next door. Very confusing. That's okay. That's okay.
Well, he'd asked me so maybe she's meant to have a son today, and
No. No so. Very, very confusing. That's okay. That's okay. Let's see. Subunits will arrange themselves with specific geometry, which is called the quaternary structure. So here, it's not as beautiful in black and white as it is in your textbook. But this is a protein that has 4 different subunits. Yeah, if you have crayons or colored markers, you can shade them in 4 different colors. I know several of you have different color things. Yeah?
What do you call it when there's like you have some of the same subunits and some that are different?
Hetero. Either all 4 are the same and that's homo, or anything that's not that has to be hetero. So the forces that hold our subunits together in a quaternary structure are similar to those used for our tertiary structures. So anyone remember from 48 hours ago, any of the forces, we could use a covalent bond. Ionic, We're going to call disulfide and covalent really in the same category. Ionic, 2 more. Hydrogen bonding. Dipole, not as strong. There's one other one that's more like a something force. I'm going to go with hydrophobic. Hydrophobic. After polling the audience, I'm going to go with my own answer. Or hydrophobic interactions, or whatever it means, so that your polars are on the outside and your hydrophobics are on the inside.
What does it say for covalent?
Disulfide. So an advantage of a multi-subunit protein we're going to go with two big advantages. So a cell is going to build all of one subunit at the same time as building another subunit, right? Builds all four at the same time and then brings them together. What if one of your subunits is folded incorrectly? Does that affect the other three? It would if you're able to even bring it in. So if we have one folded incorrectly, we can easily replace this subunit, and we don't have to replace the whole protein. Does that make sense? Like if one tire on your car is bad, you don't have to replace all four tires. You can replace just the one that's bad. Yeah.
That just naturally happened.
It would. There's kind of checks and balances in the system that if one did get misfolded, it wouldn't. It shouldn't be part of the whole subunit. Then the other one that is not nearly as intuitive so interaction between subunits will allow for the subunits to influence the behavior of the other subunits. How many people have studied hemoglobin in any other class? Great, that's all chapter 5. So we're going to look at hemoglobin again.
Is that like the affinity?
Yes. So hemoglobin is this picture right here. It's a 4-subunit protein. And when oxygen binds to one of the subunits, it forces the other 3 subunits to also want to bind oxygen. So the behavior of one subunit causes kind of a ripple effect in the other 3 subunits. So all through chapter 5, we'll do myoglobin, hemoglobin, and then some other crazy proteins. Questions on quaternary? Okay. I have 2 quick slides about lab techniques. Since I don't think anyone here is taking lab, are they? Is anyone planning on taking, you're taking the biochem lab now?
Yeah.
Okay, 1 now, 2 now, 2 in the future? Okay. So since the 2 people in lab now apparently are now experts at ion exchange chromatography and size exclusion chromatography, since that's what you're doing in lab tomorrow, a lot of exclusion chromatography. I'll be real quick in this part, because if you're not taking lab, it's not really as important. So chromatography is a way of determining amino acid sequences. There are 2 typical ways we could do our chromatography, and they are named in ways that you probably can figure it out. So size exclusion is based on size. So size exclusion, these pictures are in your textbook, so if they look really tiny, that's okay. Size exclusion has a column filled with tiny beads, and all the tiny beads have holes in them of equal size. So if you're zooming in, you would have This is my bead, and there'd be a pore going this way and this way, where the pores or holes, or whatever you want to call it, are equal size. The proteins then start at the top of my column, and based on their size will either come out fast or slow. If I have a big protein that looks like this, can that big blobby thing get through my hole? This. No, it's going to go around. Based on that, is it going to come out fast or slow? Fast. Bigger proteins come out first. Right, because they can't go through the hole, so they're just going to go around. And what about my little tiny protein? It looks like a dot. Through the hole or around the hole? It's going to go through. And because it's going to go through, it's going to go through every single hole, which means it's going to take a lot longer for it to go through. And I'm going to use the bigger and smaller because obviously those are very relative terms compared to, I'm looking at how big my bead is and how big the hole in the bead is. So just larger, smaller, bigger, smaller. So that's one way we can separate out a variety of different proteins if I had a mixture of proteins. This is just based on size. Any guesses on what ion exchange separates based on? Charge. So this separates based on charge. This separates on size. So in this case, I'm going to fill my column with beads that have a charge on them. So either negatively charged or positively charged. Let's say this is my picture of a column and it's filled with negatively charged beads. Right? So I filled my column with negatively charged things. I'm going to pour in a protein. Two proteins. I'm going to pour in a mixture of two things. One that's positively charged, one that's negatively charged. Which one will come out first? The negative is going to come out first because it hates being in that column because everybody else is negative. So it's going to zip on through as fast as possible. So the first thing to come out would be my negative. What's happening to that positively charged one? It's hanging out with everybody. It's coming over here, and it's like, oh, I got some over, and then it's going over here, and it's taking its sweet time because it's having a great time hanging out with the negative column. So then, in order to get it off, that's what's saying high salt. What I do is I add a ton of counter ion, and then the column would prefer the counter ion to the big blobby protein. So eventually, the big blobby protein comes out over here. So, one way to separate on size, one way to separate on charge. And I'm going to skip this last page.
Why does it count the positive?
Because if my high salt has a lot more pluses, right, because the blob has really like one, it's like +1, which means that each one of these beads isn't getting its full charge requirements. If I then put in a ton of positives, it will prefer the ton of positives compared to just the one. All right, and we're going to skip this last one about Eggman degradation because you don't need to know that. Go ahead and put a big X through that slide if you have it. So that we can have time to do our activity. Yay! All right. What I'm going to have everybody do is get into your groups of 3 or 4, whatever your Friday quiz group is. And if you forget, I have my handy dandy sheet over here. If you forgot who you're working with. All right, so go ahead and move now. Where are we going to move?